we'll discuss any doubts and difficulties in system of particles, collisions, etc. first, and then we'll move on to rotational mechanics as we finish today. So any doubts from HC Verma in system of particles? Or anything from the module? Any questions? Okay, Norman. So let's start with the discussion of these questions. Okay, so let's start with the discussion of this. Just give me a minute. I'll pick up the book. Okay, so question 54 has this kind of a situation. We have a smooth horizontal kind of surface, then sort of ends in a curved surface like this, which again becomes horizontal surface like this. Now from here, a block of mass m is pushed. It slides down this frictionless surface, and at the bottom of the surface there's a block B which has mass 2m. And then person lying here also is etched like this. So the thing is, we have to push this such that it has some initial speed u like this, so that after making a perfectly elastic collision with this, okay, B makes a collision with the person's head. Okay. So we have to find the minimum value of u, so that after impact B hits the person's head. So the thing is, though the question doesn't depict that way in the diagram, but we have to assume the size of the blocks is very small compared to the radius of curvature of this surface. So that is an inherent assumption that we have to make in this problem. Okay, we have to assume that we can treat the blocks A and B like particles. So assuming the blocks A and B can be treated like particles, that is, their size is negligible compared to the radius of curvature of the given surface. So doing that, now then what we can do is we can treat this like a situation where a particle of mass m starts from here with the speed u towards another particle of mass 2m, which is at rest. So then by the time it comes and hits the particle B, just before hitting the particle B, it will have a horizontal velocity, because at this point of time the tangent to the surface is horizontal. So it has a horizontal velocity v0 and B is at rest. So that v0 we can calculate by just using work energy. So half mv0 square is equal to half mu square plus mgh. So v0 will be equal to square root of u square plus 2gh. So this is the first thing. This is the impact velocity with which A is hitting B. So Norman, it's clear up to this point? Okay. Now, next thing we have to look at the collision between A and B. So just after impact, we assume that the velocities of A and B become v1 and v2. Okay, and the masses are of course m and 2m, and the collision is perfectly elastic. So we can find out v1 and v2 from this formula. v1 is m1 minus m2 upon m1 plus m2 times u1, which is v0. Okay, and the second term is missing because, okay, and v2 is 2m1 upon m1 plus m2. So this is times v0. So this is 2 by 3 v0, and this will be minus v0 by 3. So actually what will happen is just after the impact, A will be going backwards at v0 by 3 and B will be going forwards at 2 v0 by 3. So just after impact, now next diagram, this is what is happening. So the system is going from here to now here. So B's initial velocity just after impact is 2 v0 by 3. And then what we want is B should reach this highest point. So its velocity by the time it comes here should be greater than equal to 0. Just about 0 will also do. So that means this velocity of B, this v2, that is related to this h by, again, half mv square plus, I mean, even though the mass is 2m for B, but mass anyway cancels out in the equation. So whether we write it as mass of B specifically or we write it as 2m, so from this we'll get that V square is equal to V2 square minus 2gh. Now we want V to be greater than equal to 0. So that means V2 square minus 2gh should be greater than equal to 0. Okay. So this formula where this is coming from, this is clear, Norman? I'm just directly applying the formula of 1D collisions. That, remember these formulae we had written, m1 minus em2 upon m1 plus m2 times u1 plus one plus e m1 upon m1 plus m2 U2. These were the collision formula. Similarly, V2 is 1 plus EM1 divided by M1 plus M2. So this one is M2 over here. So these are the general formulae. In that we are applying this particular collisions condition. So here we are substituting M1 as M, M2 as 2M, U1 as V0, U2 as 0, and E as 1. So that's how I've got these equations. Okay, so anyhow, now we have to satisfy this condition. So 2 V0 by 3 should be greater than square root of 2GH. Okay. So 4 by 9 V0 square should be greater than 2GH. Okay. So V0 square should be greater than 9GH by 2. Okay. And V0 in turn was how much? Square root of U square plus 2GH. Okay. So substitute that here. So U square plus 2GH should be greater than equal to 9 by 2GH. So that means U square should be greater than 9 by 2 minus 2 or 5 by 2. So U should be greater than equal to. So the minimum speed with which you have to project the particle A or the block A will have to be root 5 by 2GH. So it is like 2 times you're applying work energy theorem. Once when A is sliding down this surface, next when B is sliding up this surface. But in between the interaction between A and B, you're solving the 1D collision, for which I've written the general formula here. Or you can also do it by the equation method, that A is coming and colliding with B with the initial speed V0. So momentum conservation is the first thing we can apply. So mv0 should be equal to mv1 plus 2mv2, and then E is equal to 1. So separation velocity should be equal to approach velocity. So v2 minus v1 should be equal to v0. So if you solve these two equations also, you will get that v2 will be 2 by 3 v0. So it's up to you whichever method you use. You can use momentum conservation and coefficient of restitution fundamentals to solve the collision like I've done here, or you can use the direct formula that we get by solving those equations that I've written here. But this equation becomes crucial. Yes, exactly. It's a collision. It's a free collision between A and B. No other external agent is playing a role during the collision. There is only impact force, which is a mutual force between them. So for the system, for any collision system, always momentum is conserved, right? Okay. So Norman, I'll come back to question 55. In between, Deep has also asked question number 11. So I will go back to question 11 first, then come back to question 55. So just go through this once and note down any points you require. Okay, so let's move on to 11th question. So we have to find the center of mass of a uniform plate having semicircular inner and outer boundaries. Of radius R1 and R2. So we can do this by a couple of methods. One is by superposition method. So this type of question is very common in the center of mass part of this chapter. Calculation of position of center of mass, that part. So let's first understand what our body is like. It is like, suppose we had a large disc like this, and then from that we cut out a round hole. So from our large disc, suppose we cut out a round hole. So we are left with like an annulus of a ring kind of thing, or a donut shaped or a washer shaped thing. And then we have cut half of that. So it's like we've got a semi-annulus, that kind of shape. Or we started with a semi-disc and then cut out a semicircular hole in it like that. Okay, so this is the shape of our object, roughly speaking. Okay. Some diagrams, but anyhow, so this is so now this is the symmetry axis, right? And let's say we take this as the origin of our system, and this radius is R1 and this radius is R2, and the mass of this object is M. So it's a thin plate, so its center of mass will be somewhere over here. Let's say C is the center of mass, which will have some y coordinate which you want to calculate. Okay, so one of the things that we can do over here is that we can use superposition. That is, I have this object which is of mass, let's say M, and its own center of mass is somewhere here, y1. This is the same as this, okay. But I also have another object, which is the part that I've cut out. And its center of mass is somewhere here. Its mass is M2. This radius is R1. And if I now place both these masses together, then I'll get a full disk like this. And that disk center of mass is also at a known position. That disk center of mass is over here, let's say. Why not? So this whole system is having a total mass, let's say M0, which is M1 plus M2. So now I know that this one is equal to, now this is a disk of radius R2 now. So remember the formula for the disk, semi-disk, it is 4r by 3 pi. That's why this one's formula for the position of the center of mass will be 4r1 by 3 pi. But this one center of mass is what we don't know. And that is this only. Whatever is YCM in that is only my Y1 in the representation below. So is this representation clear, Deep?
Yes, sir.
Oh. So now the only thing is we have to replace this mass m1 with an equivalent particle at y1. Then we have to replace that mass m2 with an equivalent particle at y2. And we know that that system center of mass will be at some y0. Okay. So if we take m1 plus m2, we are getting that mass m0. So this one center of mass is at y1, this one center of mass is at y2, this one center of mass is at y0. So y0 will be m1 y1 plus m2 y2 divided by m1 plus m2. So now the thing here is that I know y0, I know y2, okay, and y1 is the unknown quantity. So I have to just calculate this m1, m2 in terms of each other and substitute. Okay, so we can even say like this, that m1 plus m2 into y0 is equal to m1 y1 plus m2 y2, or m0 y0 is equal to m1 y1 plus m2 y2. Now what should be m0? It's a full semi-disk of radius r2. So it is some surface mass density into pi r2 square. What is m2? It is a semi-disk of radius r1. So it is sigma into pi r1 square. Okay. And what is m1? This is the one with the hole. So it is sigma into pi r2 square minus r1 square. Only thing is these are all divided by 2 because they are semi. So there's a division by 2 everywhere. So are these three clear, Deep?
Yes, sir.
Okay, so now we'll just substitute this. Okay, so you will see that we can take sigma pi by 2 common everywhere. So here we will have r2 square into y0, which is 4r2 by 3 pi. So again taking sigma pi by 2 common. Okay. So y1 is the unknown quantity, but m1 has a factor of r2 square minus r1 square into y1, and m2 has a factor of r2 square into a factor of y2, and y2 was how much? It was 4r1 by 3 pi. Okay, this is y2, this is y0, y1 is unknown. Okay, so now we can get the value of y1 from this. So 4 sorry, so become 2 by 3. Okay. R2 cube, right? Pi will cancel, sigma will cancel. Or let's keep this pi because we're cancelling this pi on both the sides. So this one, so we're cancelling this and this. Oh, so then this will become 4 by 3. Sorry. So 4 by 3. Yeah, 4 by 3 r2 cube by pi should be equal to r2 square minus r1 square into y1 plus 4 by 3 r2 square r1 by pi. So y1 will become like this now. 4 by 3 r2 square by pi I can take common. I'll be left with r2 minus r1 upon this denominator, which is r2 square minus r1 square. So then just expand this as r2 minus r1 into r2 plus r1. So y1 you'll see will become 4 by 3 pi r2 square upon r1 plus r2. So this is the original y coordinate of the center of mass above, because that is what we had reduced to y1. Okay, Deep, so hope this method is clear.
Yes, sir.
We just check the answer also once. So it's 11th question. No? The answer is something else. Just a minute. Why the answer is not matching for us? Let's just check. So have we substituted M1 plus M2 correctly? Yes. Sigma pi by 2 into R2 square. 4R by 3 pi. Okay. We just have to check this once why the answer is not matching. Let's go over this. This is correct. Okay. Then this mass,
Sir.
yes.
Sir, R2 minus R1, the whole square will come, no?
Oh yeah, this is where the mistake is now. M2 depends on R1 square. This is not R2, this is R1. Yes, this term I've substituted this wrong here. No? This is M2 into Y2. Now M2 also depends on R2 square. No? And Y2 is also 4R1 by 3 pi.
Yes.
Understood? So this has to be corrected. So then we'll get a R2 cube minus R1 cube type of, okay, which we can factorize. Okay, so we'll get that answer. So this is sigma pi by 2 R1 square, okay, into that 4R1 by 3 pi, this kind of term. So now we will get this. We'll get 4 by 3 pi R2 cube is equal to R2 square minus R1 square to Y1 plus 4 by 3 pi R1 cube. So Y1, as you can see, will become 4 by 3 pi R2 cube minus R1 cube divided by R2 square minus R1 square. So you can leave the answer this way also, or you can factorize like done in HC Verma. So R2 minus R1 into R2 square plus R1 R2 plus R1 square divided by, again, R2 minus R1 into R2 plus R1. So this will become, yeah, so if you've written this down, please make sure that you incorporate the correction I've just made. Okay, so Deep, hope the question is clear by this method.
Yes, sir.
Okay, now there is one more method you can apply, which is also not too difficult. That is like more like the fundamental derivation method type of thing. Okay. Just like we're done for the semi-disk, but only the limits of integration will change. So this semi-annular ring, what we'll do is we'll slice it into thin rings and integrate for the thin rings. But the radius going from R1 to R2 instead of 0 to R. So once again, we understand that this is a symmetry axis. So the center of mass will lie on the symmetry axis. So now what we can do is at some arbitrary radius small r, which is in between R1 and R2, we'll slice a semi ring like this.
Sir, we have done this type of questions.
Sorry, you're done?
We have done this type of question.
So that only. Okay, we've done the derivation of the semi ring one. So dr, okay. This is R1, this is R2. So now the y coordinate of this one's center of mass, the semi ring center of mass. So this is a semi ring of mass sigma into dA. So that is sigma into 2 pi r dr. And its y coordinate will be 2r by pi. So now the y coordinate of the entire system center of mass will be integration by dm divided by total mass, which is integration dm. So that is integration 2r by pi into sigma into 2 pi r dr, integrated from only difference is now r1 to r2 divided by sigma into 2 pi r dr, integrated from r1 to r2. So next step, you take out all the constants and all that. So 2 pi sigma, all this gets cancelled. So we have 2 by pi coming out from here, and in the numerator we have r square dr from r1 to r2, and in the denominator we have r dr from r1 to r2. So this becomes 2 by pi r cube by 3 divided by r square by 2 from r1 to r2, from r1 to r2. So that's how you will see it will become 4 by 3 pi into r2 cube minus r1 cube divided by r2 square minus r1 square, which after the same factorization becomes the same thing, that 4 by 3 pi so this is also an option. In fact, if you ask me, this is the, even though this involves an integration, this is the shorter option because the integration is quite easy to calculate. Whereas in that whole superposition method, we have to separately substitute the masses, cancel the common term, and also it was a little bit tedious. Okay. Anyhow, so hope this is clear. Also, okay, Deep, let's come to question 55 next. I'll come back to your other questions also, Deep. Okay, let's first come to question 55. So in that we're having this kind of a situation. A bullet of 10 grams is moving horizontally at a speed of this much, strikes a block 490 grams kept on this frictionless track as shown. Bullet remains inside the block and the system proceeds towards the semicircular track of radius 0.2 meters. Where will the block strike the horizontal part after leaving the semicircle? So this is a bit of a lengthy calculation. Now we have to actually work out each of the things carefully. So this is like a fixed track now. Okay, this is fixed. And this radius is 0.2 meters. And we have to assume that its surface is smooth. And there's a block sitting here first. That block is hit by a bullet, which is moving with a velocity v0. Okay. So the bullet's mass, let's say small m, is 10 grams, and the block's mass is 490 grams. The bullet speed is 50√7 meters per second. Now the bullet gets stuck inside the block. So once it gets stuck inside the block, it's like an inelastic collision. So the total momentum of the system will remain conserved with the bullet stuck inside the block. So m plus m into v will be equal to mv. Okay. So this will become 10 upon 490 plus 10 times v0. That's v0 by 50. Okay. Or it will be √7 meters per second. Now, once this happens, now we can see it reaches here with a speed v. Okay. So by the time it reaches somewhere here, where it's about to lose contact, let's say the speed has become v prime. So this angle is theta. The condition for it to lose contact at this point is that, okay, so if the normal reaction is 0, so at that point, n is equal to 0 means mg cos theta is equal to mv prime square by r. And from, let's say, this point to this point, apply work energy theorem. So A to B, half mv prime square minus half mv square, that is the change in kinetic energy, plus mgh is equal to 0, where h will be equal to this height from here to here. So that you can see is r plus r cos theta. So our second equation, so this standard stuff which you've done in vertical circular motion. Okay. So v prime square will become v square minus 2gr into 1 minus cos theta. Sorry, 1 plus cos theta. And this will give us that v prime square is equal to 2gr cos theta. So solving this and this together will tell us that v prime square is equal to, sorry, gr cos theta. Okay, so now we substitute this value here. So √7 square minus 2 into 10 into 0.2 is equal to 10 into 0.2 cos theta. So 7 minus 4 into 1 plus cos theta is equal to 2 cos theta. So 7 minus 4, that's 3, is equal to 4 plus 2, that's 6 cos theta. So cos theta is half, which means theta is how much? 60 degrees. So it loses contact at the 60-degree point. So from there, what happens? It goes into projectile motion. So next part of the question we have to solve is the projectile motion from the point B till it hits the ground. Okay. So just make a note up to this first. So first we are solving the inelastic collision, or the condition for the bullet to go and get embedded in the block. We are solving that to find out the speed with which the block starts moving with the bullet embedded towards the semicircular track. So that came out to be √7. That was this first step over here. Then what we are doing is we are looking at the motion on the semicircular track. starting from the bottommost position where the speed is this v only, √7, till the point B on the surface where the normal contact force becomes 0. So we have the condition for n to become 0. That gives us a dynamical equation or Newton's laws equation. That's this. And we have the condition of work energy between A and B, mechanical energy condition. So that gives a relationship between V prime and V. So solving these two, we substitute this value of V at the bottom as √7. We substitute the radius as 0.2, and it comes out that the angle at which the contact loss is happening, the theta with respect to the vertical is 60 degrees, or cos inverse of half. Okay, so just go through the steps or note down up to this point. We'll discuss further. Okay, so now I hope it's clear up to this point. Okay, now the last part of the motion from B till it hits the blank again. So we have to solve. So this is where it loses contact. Now when it loses contact, its speed was, remember, V prime. So it go in a path like this. So this V prime will be at the same angle to the vertical. This angle is 90. So this angle will also be 60. So the projectile motion from B, for that projectile motion, the initial speed is actually this V prime, which you'll remember is square root of gr cos theta. So from this equation above, this equation C. So it's square root of gr cos theta. So it's square root of 10 into 0.2 into cos 60. So it is 1 meter per second. Okay. And this one's horizontal component is u cos 60. So it is 0.5 meters per second. And its vertical component is u sin 60. So that is 0.5 √3 meters per second. Okay. Now, what we can do here is we have to find this point's location, right? So let's do like this. Let's take this point only as our origin. Okay. So we can see that from here to here, if this distance is some d, okay, and this distance is how much? It is r sine 60. So it is root 3 by 2 r. So the x component of displacement when it hits over here is equal to how much? It is d plus root 3 by 2 r. So that is the unknown d plus root 3 by 10, because r is 0.2. Then the y component of displacement from here to here is negative of this total height. So the y component of displacement is minus of r 1 plus cos 60. So now we can use whatever equation of trajectory or time-based equations or whatever. So x is ux into time, y is equal to uy into t minus half dt square. So we can use this kind of relation, or we can just use this one. So actually, this is easier. Now, what we'll do is from this second equation, solve for time. Okay. You'll get two values, one negative, one positive, and then put that back in equation one. So then you solve that for t. So the time-based equations will be easier over here. Equation of trajectory will become unnecessary. It will become too lengthy. So don't go for equation of trajectory. Don't go for this. Instead, go for this method. Is it clear, Norman?
Yes, sir.
Okay. So these type of questions are pretty lengthy, and you have to understand that they will take time and a lot of energy to solve. Okay. But through the question, you are revising a lot of concepts. The collision part was very small. The collision between the block and the bullet, you got that speed to be √7. The collision part is finished over there. But from there on, the concept of vertical circular motion, the loss of contact, okay, and then finally the last part, you're going back to projectile motion. So that's why these questions are very helpful in revising all multiple concepts together in the same thing. So don't worry if they take you time to solve, or if it's a little frustrating initially. Just keep at it and you keep learning. Okay, since we are in this section, let's do question 56 also. Yes.
Sir, can you scroll up?
Yeah. This part?
Yes, sir.
Yeah.
Done, sir.
Next we do question 56. Then we come to few of the questions in the previous page. On this okay, so go through question 56 next. So again, take you through it. It's the same thing. Now you'll realize that when the two bobs, or the two small balls that you release of mass m and 2m, they will both simultaneously go into vertical circular motion, because they are connected by thread. So they will have like mirror image type of motions of each other. One will have a sort of clockwise circular motion, the other will have an anti-clockwise circular motion. But their kinematics will be identical, I mean mirror image of each other, but the time taken for them to reach the lowest position will be identical because that's independent of mass. But when they reach the lowest position, they will collide against each other, and that collision will be head on because both their velocities will be just about horizontal. Because as they reach the lowest position, the string is at 90 degrees to the horizontal, so the velocity will be along the horizontal. Both the threads will be almost vertical. Okay, so their velocities will be almost horizontal. So they make a head-on collision. Head-on collision, which again I think is perfectly elastic. So it's again that type of collision, two bodies of mass m and 2m making a perfectly elastic head-on collision. But unlike the question we did previously, there one of the objects was at rest. Here both the objects are moving towards each other. So you have to solve this in basically in three parts. First is the independent circular motion from the horizontal position to the nearly vertical position just before collision. That's very easy. That will give you the velocity as root 2 gr for each one. R in this case is the length of the thread. Then you have to solve the collision using those standard formulae. So then you get the velocity just after impact. And again, you have to solve for the vertical circular motion because you know the velocity just after impact. So from that, you can solve the vertical circular motion after impact. Just go through the question 56 and try this out. We'll discuss in a moment. Okay, so let's move on with this question. So initially you release them from this position where the strings are tied to this point. And this one is having mass m and this one is having mass 2m. So by the time the strings are about to become vertical and they're going to collide with each other, the velocity is just before impact. Like this. This has a velocity in this direction. And this has a velocity in this direction. The magnitude of the velocity is √2g. So now we have this kind of collision. This is coming towards this is coming towards this, and they both have the same magnitude of velocity. So after impact, immediately after impact, their velocities, let's say, become like this. B has a velocity of v2, A has a velocity of v1. So we substitute with sign convention and all over here. We will take m1 as m, m2 as 2m, u1 as plus u or plus v, where and u2 as minus v. And it's a perfectly elastic collision. So just after impact, v1 will become m1 minus m2 upon m1 plus m2 times u1 plus 2m1 upon m1 plus m2 times u2. So this is minus 1 by 3 minus 2 by 3. This is 2m1. Oh, sorry, it is 2m2. So this is 4. This is minus 4 by 3. So this will be a larger velocity. So this is 2m1 upon m1 plus m2 plus m2 minus m1 upon m1 plus m2. This is 2 by 3 minus 1 by 3. That means just after impact, B is having a velocity like this, V by 3. And just after impact, A is having a velocity in this direction of 5V by 3, where V is √2gl. So from this, you'll understand that A is having a velocity which is greater than √5gl, right? A's velocity, if you compare 5 by 3 √2gl. So if you take this thing inside, it is 25 by 9 into 2 gl. So that is 50 by 9. So VA is greater than √5 gl. So it will complete vertical sublimation. Correct? whereas B will
Yes.
oscillate like a pendulum, okay, because its velocity is less than √2 gl. So B will come to rest somewhere at some theta, which you can calculate by just making the kinetic energy 0. Okay, so you can complete the last part yourself. The maximum displacement to which B will go somewhere here, it will stop, whereas A will complete the vertical circular motion. So it will reach the 2L point and move. Right, Norman? So hope this is clear also. Okay, let's come to question 61, which again Deep has asked. So 61 is a simple case of conservation of horizontal linear momentum for the system and conservation of mechanical energy because there's no friction anywhere. Okay, so just go through the language of question 61. So this wedge is like this, let's say. Okay. All surfaces everywhere are frictionless. Now this small block of mass m, which is on the horizontal section of the wedge. So this is also a smooth surface. This is also smooth. This is set off with some velocity v0, let's say. Which they've taken as v. Okay. So what will happen is for the system m plus m. Okay. In a general situation like this, when this block comes somewhere here, you can see that there is contact force like this, but that's a mutual force. Okay. Whereas the external forces are the weight of this block, and the normal reaction with the ground. So all external forces, that is small mg, capital Mg, and n prime with the flow, are vertical, either upwards or downwards, but they are vertical. So hence, what will happen is the horizontal component of momentum is conserved. Therefore, horizontal momentum is conserved for this system. That's one thing that is conserved. And the other thing is that the sum of kinetic energy plus gravitational potential energy is conserved. That is the mechanical energy. That is conserved. So now we have to just compare this, that for example, this is the initial state of the system. Now, after some time, if the situation has become like this, that this block has now come here. So by that time, the block has a relative velocity, which is VR like this. But the block is in contact with this, so they have this. Okay. So when the block small m is on the vertical surface of the wedge, capital M. So this part is the vertical surface. At that point of time, let's say VR is its relative velocity with respect to the wedge. Okay. And V is the horizontal velocity of the wedge. Okay. So that point of time, if you take this as your X and Y axis, you can see that the velocity of the wedge with respect to the ground frame is minus VI cap. But the velocity of the block with respect to the wedge, that is equal to plus VR J cap. So from this, you can understand that the velocity of the block in the ground frame is the relative velocity plus the velocity of the wedge. Okay. So the velocity of the block in the ground frame has the horizontal component minus V and the vertical component VR, like this. So what is the horizontal momentum of the system? So horizontal momentum for the system is this is the horizontal component, or we can just write it in magnitude as in the backward direction like this. Whereas initially in the above picture, you had seen that the horizontal momentum of the system here was mv0 in the backward direction. So this horizontal momentum should be conserved. So that is what answers the first part of the question. So mv0 should be equal to m plus m. So Deep, this part is clear. This is the first part of the question.
Yes, sir.
Okay. Now the next part, by the time the block reaches this position, so by then what is happening is that its vertical component of velocity would have reduced even further because it's going against gravity. So by the time this is reached here, this one's relative velocity has, let's say, become some v prime. This v prime, this is relative to the wedge. So that is v prime, and the wedge is moving with the same horizontal velocity v as earlier, because that is not getting affected now. So compared to its initial position here, the gravitational potential energy has increased by how much? H, like this. Okay. So from initial to final, when we apply conservation of energy, mechanical energy, we can say that change in kinetic energy plus change in gravitational potential energy is 0. So this is plus mgh. Okay, but what is this? This is the block's kinetic energy plus the wedge's kinetic energy. Okay, minus of the initial kinetic energy, which was only of the wedge, or only of the block. Okay. So in this, you can see that the velocity of the block at this instant is minus vi cap plus v prime j cap. So the speed of the block is square root of horizontal component square plus vertical component square. So substituting in this equation now, we'll see that half m v square plus v prime square plus half capital M v square. So this is the final kinetic energy minus half m v naught square. This is the initial potential energy. So this is the change in kinetic energy plus mgh. This is the change in potential energy. So this should be 0. So now here in this equation, we've already seen V is this. So substituting this, so like this, and now this V is m upon m plus m. V naught. So when you work out this term, you'll see you'll get this as m upon m plus m. So just take square root of the other side, and that will give you V prime. Okay, so that is the 61st question. Okay, so this is giving you that V prime term. So you'll also have to find the speed of the smaller block, you'll also have to take the horizontal component of it. Okay. But see, directly if you want to find the speed of the smaller block, you can also do it from this. You can see that half m v of the smaller block square plus half capital M v square minus half m v naught square plus mgh is 0. So from this you can see that you directly do this. Okay. And in this now substitute v as this. So then you'll get the type of answer that they've expressed. Okay, and the rest of the things is kinematics from this point onwards. So once you get this V prime, you can see that the maximum height to which it will prime is V prime square by 2g by kinematics. Yes. So again, the calculation part is a little lengthy in this type of question, but you have to break it down part by part. So the conservation principles here are horizontal linear momentum is conserved and total mechanical energy is conserved. So anyhow, Deep, hope this is clear. Okay, you also had a doubt in the 28th question, so I'll explain that next.
Sir,
Yes.
sir, 28 is not a doubt, sir.
Okay, not a doubt. We're done. Okay. So fine, we are done with the doubts for center of mass or system of particles now. Yes. Okay. So Deep, your doubts are done, right? Because you had sent to me 11, 28 and 61. So I hope you have completed 28 yourself.
Yes, sir.
Okay, good. So fine. So let's move a little ahead now. Let's look at some basic concepts of rotational mechanics today. You can continue doing problems from the module also of system of particles, center of mass. It's a lengthy chapter, so it might take you a couple of weeks to complete all the problems and all that. So maybe we'll keep aside some time in the next lecture also for doubts. But presently, let's start with the next chapter, which is rotational mechanics. So this is also in certain cases, this is also called rotational dynamics. Okay. Or it is also called rigid body mechanics. So here we want to first of all understand the different types of motion for a rigid body. Then we'll understand how rotational mechanics will be applied. So types of motion for a rigid body. Now, typical example of rather straightforward kind of rigid body we can think of is something like a rod, let's say. Okay. Now, if a rod moves in such a way that it might have its center might be traveling in this kind of path, but its orientation is never changing. So, it's moving in such a way that it's now like this. So if you see, it's not rotated, it's only translated. So this is at some time t plus delta t. And this is where it was at time t equal to 0. Oh, sorry, t equal to t, let's say. So in this case, you can see that the rigid body has moved in such a way that if you look at any point on the rigid body, like let's say this corner is A. So this corner has moved to this point now. Okay. The center has moved to this point now. If you look at this corner, let's say B, that has moved to this point now. So every point has the same displacement. So this type of motion is called pure translation. The definition of pure translation is it is the motion of a rigid body such that there is no rotation with respect to or no rotation of the body when observed from the reference frame of its center of mass. So I've taken as C. So if you are traveling along with its center of mass, if this is your reference frame, then you won't observe any rotation. In fact, the body will be at rest. So in other words, in its center of mass frame, the body appears to be at rest. So another important property from that of pure translation is that in case of pure translation, every point in the rigid body has identical motion that is displacement or velocity or acceleration with respect to any frame. So for example, if we are observing this from the ground frame now, so as the rigid body moves like this from this point to this point to this point, so its center of mass is going like this. So any point on the rigid body, like this corner point A, is finally moving to this point A prime. So whatever the displacement of this corner point, any other point, let's say located over here, will have the same displacement. Okay. So at this instant, whatever is the velocity of this point A, same will be the velocity of this point B. Whatever is the acceleration of this point A, same will be the acceleration of this point. So any 2 points let's say A and B move such that the displacement of A is equal to displacement of B, velocity of A is equal to velocity of B, the instantaneous acceleration of A is equal to the acceleration of B. Okay. So that type of motion is classified as pure translation, and therefore to describe the dynamics of pure translation, okay, we can treat the entire rigid body like a particle located at its center of mass. Okay. So therefore, for the dynamics of pure translation, the rigid body can be treated like a particle of its equivalent mass at its center of mass. So basically then we apply particle dynamics to it. And that's what we've learned till now. Newton's laws of motion, okay, work power energy, system of center of mass concept, all this. This has all been with regard to particle dynamics till now. But now we are moving ahead. We'll see that this is not the only type of motion possible for rigid bodies. There is also motion of rigid bodies possible in which there is rotation involved. So in that we cannot apply particle dynamics anymore. Okay. So anyhow, before we get into that, just make a quick note of this. This is an important thing, the definition of pure translation. So we are looking at different types of motion of a rigid body. So the first type of motion we will see is pure translation. And below is the definition and the explanation of pure translation. How do we recognize whether the motion of a rigid body, we can classify it as pure translation or not? So one way is that we can get into the center of mass frame of the rigid body, and in that frame it should not be rotating, it should not be moving at all, it should be at rest with respect to its center of mass. Another way is we can understand that from any frame, the ground frame or any other moving frame, we can trace the displacement, velocity, acceleration, or the entire kinematics or the motion of 2 or 3 different points on the rigid body. We can say with confidence that all the points on the rigid body are having identical motion. That means they are having the same displacement at a particular instant. They have the same instantaneous velocity. They have identical acceleration. Then again, we can say that, okay, that means there is no rotation happening. All the particles that are part of the rigid body are moving like one common particle located at the center of mass. So that's another definition of pure translation. And the moment we are sure that the motion is pure translation, to apply dynamics, that is whether we apply Newton's laws of motion or work by energy or the concepts from center of mass that we've learned, we can treat the entire rigid body like an equivalent particle located at its center of mass. Okay, so this is very important. This is the definition of pure translation. And whenever we have pure translation, we don't need to apply the equations that we're going to learn in this chapter, that is rotational mechanics. We can apply the equations that we've learned previous to this chapter, like net force is equal to mass into acceleration. Okay, work done by external plus non-conservative is equal to change in kinetic plus change in potential, work power energy, and so on and so forth. Okay, now let's come to the next category of
Sir,
rigid. Yeah.
sir, I was just copying the right side of the.
Okay. Okay, done now.
Yes, sir. Done.
Okay. Now let's look at the next type of rigid body motion.
Sir, so in that rotation is happening, but in center of mass frame it is not happening.
Which one?
Sir, in first case, pure translation.
No, pure translation, there is no rotation happening. You see how this body is moving? It's not rotating, no? It's just moving like this. See, like, wait a minute. Okay. Yeah, now just follow me. Like, treat this pen as the rigid body. If it is moving in this way, you can see there's no rotation happening. It's pure translation. When we'll say there's some rotation happening, when something like this is happening. Understood?
Yes, sir.
So now we'll see that there are now rotation also we can break into two categories. Like if the rotation is happening about a fixed axis, like the motion of a pendulum, like this is rotating like this now. So every particle in the rigid body is rotating about a common fixed axis. Then it is called pure rotation. Whereas if it is moving in such a way that the center of mass is translating, but about the center of mass there's also rotation happening, then it is called the general rigid body motion, which is basically a combination of both translation and rotation. So in that case, there is translation also happening, and while translation is happening, simultaneously there's rotation happening about its center of mass axis. So the body is moving like this in a combination of rotation and translation. Understood the difference between the two?
Yes, sir. Understood.
Okay. So for example, a block sliding on a horizontal surface or even sliding down an inclined surface. This is an example of pure translation. Okay. But if I make it topple over like this now, so you can see what is happening. It's moving in a combination of rotation and translation. It's doing something like this. Okay. Or if I just flip this object like this, so it will go in projectile motion. But while it's going in projectile motion, it will also be spinning about its center of mass. So that is the combination of rotation and translation. Whereas if I attach it to a fixed axis and release it like this, then it's pure rotation, because it's rotating about a fixed axis.
Yes, sir.
So first we discuss about the pure types of motion, the pure translation, which we've just discussed, and now the pure rotation. And then we see that in a general case, it is neither of the two. Neither it is pure rotation nor it is pure translation, but it's a combination of both the things happening. And that is called the general rigid body motion. Because when there is no constraint, like a fixed axis or that it has to translate purely, then the general type of motion of a rigid body happens in which manner? It happens in the combination of rotation and translation. Okay. So as I said, first we'll discuss the pure types of motion. So the first pure type of motion we saw was pure translation. Now next we look at pure rotation. So just like pure translation has a very simple definition, so does pure rotation. Pure rotation is when there is rotation about a fixed axis. So this is the type of motion of a rigid body when it rotates about a fixed axis. So in that case, what happens is every particle within the rigid body, every particle or point in the rigid body is in circular motion about a common fixed axis. Okay. So whether it is a case of a rod which is rotating about a hinge on the wall like this, let's say. Okay. So if the rod is rotating like this, then after some time might have taken this kind of a position. So you can see that all points within the rod are describing circular paths, and all of them about a common axis. They're all describing circular paths. So they might be having individually different distance traveled. They might be having individually different amounts of velocity. Like this one will have a tangential velocity, which is more than the tangential velocity that this one will have. But their angular parameters will be the same. Now, the angular speed of one will be equal to the angular speed of the other. The angular displacement of one will be equal to the angular displacement of the other, and so on and so forth. Okay. So it could be something like this, or it could be the case of like we have, let's say, a sphere which is spinning about its own diameter. So this is also an example of pure translation, because pure rotation, because every particle is describing a circular path about the common fixed axis. So these are all examples of pure rotation. Fixed diameter.
Means all centers are collinear, no?
Sorry, all the
Centers are collinear, no? Of all particles.
coming in all water collinear, all paths.
Sir, center.
Center of what, beta?
Sir, it is forming circle, no? Circular.
All the centers are, yeah, all the particles are moving in circular motion, where their centers are all lying on a common fixed axis. Yes, so they're all their centers together will form one line. That is the axis of rotation. That's the fixed axis. Yes, so the centers of their circular motions are collinear. You can say that. That's correct. So now the important thing to keep track of in pure rotation is that the displacement, velocity, acceleration, etc. are not identical for different particles. Okay. So the further away from the axis a particle is, the more magnitude of velocity it will have. Okay. Also, acceleration will be a combination of centripetal acceleration and tangential acceleration. So that will again depend on the distance from the axis, like that. But the angular parameters of their rotation are identical or common for all the particles. So what are the angular parameters? The same we had learned in circular motion. Angular displacement, okay, angular speed, angular acceleration. They are going to be the same for all particles, part of the rigid body. Okay, so this is clear.
Yes, sir.
Now we come to the more,
Sir,
you know,
1 minute.
yeah. Now we come to the most common situation which we observe in everyday life. Okay, which is the combination of rotation and translation. So whether we are, looking at the, for example, orbital motion of a satellite around the Earth, or the way the moon is moving around the Earth, or the Earth itself in its orbital motion around Sun. So something reasonably complicated like that, or something very simple like a cylinder rolling down an inclined plane, or a stick which you've just flipped in the air. So the center of mass of the stick is moving in a parabolic projectile motion. But while that is happening, the stick is rotating about the center of mass. So all these types of motions, they are a complex combination of both translation and rotation. So how to deal with translational motion, that we have learned till now in mechanics, right from kinematics equations that we wrote, right up to work power energy application and certain parts of center of mass. That was all about translation. Now, how to deal with rotation, that is the first part we learn in this next chapter of rotational mechanics. And when we have learned how to deal with pure rotation, then we will learn how to deal with the general rigid body motion, which is both the things happening simultaneously. Now, it's the superposition of translation and rotation. On the one hand, the center of mass is translating, and on the other hand, while that is happening, about the center of mass, there is also rotation happening. So this is like the
Done,
final
sir.
part of mechanics, right? Where we'll put together all the concepts that we've learned. So general rigid body motion. This is a combination of translation plus rotation. Okay, so that example that I gave you, that you throw a stick in the air while it is also spinning. So its center of mass has been given some velocity, but about the center of mass, there's also some angular velocity. So as it moves, it has this interesting kind of path. It is somewhere here. It's like this. By the time it's here, it's now like this. So all the time spinning about its center of mass, while also the center of mass is traveling. So its center of mass has some velocity vcm, and about the center of mass there's some angular velocity omega. So its center of mass will be in a parabolic path, which we know how to describe by projectile motion. Whereas, and the stick itself is rotating about an axis. To its center. So there is a combination of translation and rotation. Or you take the example of a cylinder or a drum rolling down an inclined plane. So its center of mass will describe a path like this. There's a velocity like this, but about the center of mass, the body is also spinning. So the center of mass is having a linear or one-dimensional motion down the incline, and simultaneously the whole body rotates about the center of mass axis of the cylinder. So these are just two examples, and almost every other motion of a rigid body that you see in everyday life is some kind of combination of rotation and translation. Okay, so hope you understood this part.
Yes, sir.
Okay, so we will conclude our session here today. Now, next time we will start with the study of pure rotation. Okay, because pure translation is something that we've been doing till now in mechanics. So we'll start with the study of pure rotation, that is rotation about a fixed axis. So first of all, we'll see that the kinematics or the motion, the equations of motion itself can be described by the angular parameters, just like we did in circular motion. So relationship between angular displacement, angular position, then angular velocity and angular acceleration. So these all things will become important when we look at the kinematics of pure rotation in terms of the angular parameters. And from there, we will see how to describe the velocity, acceleration, etc. of different particles. And from there, we'll understand how to apply dynamics. So when we apply dynamics to pure rotation, we'll see that there's some quantity called torque, which is moment of force. Okay? So these are the things that will be coming up in the next lecture. So please do a quick recap of circular motion if possible before the next lecture, because the various things that we had learned in circular motion, including the angular parameters, then the relationship between centripetal force and or rather centripetal acceleration and angular velocity and things like that, they'll become important as we look into the details of pure rotation. So just do a quick recap of circular motion and related definitions and concepts before the next lecture. That's it for today's session, people. Thanks for attending and wish you all the best.
Thank you, sir. Bye, sir.
Bye, people.
Thank you, sir. Bye, sir.
Bye. Bye.